first is, when I was a lowly graduate student and we first met, he was always willing to provide time, which is not necessarily seen everywhere these days. People are very, very busy. So Thomas actually reminded me that I saw him one Christmas vacation at Caltech, and he actually, I think, made the whole day for me that time. When I visited his lab subsequently, we were collaborating in Sandia. I would always notice that there was a really nice mix of undergraduates, graduate students, and postdocs and faculty, kind of all in the same space and all working together in a way that I guess I can only describe as old school. And I think that always struck me as a really fantastic thing. Thomas is well known as the father of the Beowulf cluster, which is arguably the way that we do high-performance computing these days. I met him as part of the hybrid technology multi-threaded HTMT project, which was the sort of definitive opposite of Beowulf cluster, which I think shows his range of intellectual depth. And I would say that as a student, I think it was the best project that I worked on, and having seen a lot of projects since then. In some sense, in my mind, it's often the model of success, because I remember at the time, my colleagues were all studying branch prediction, which is a topic that has almost entirely gone away as an area of research. And we got to think new thoughts about completely different computers. And that was always very, very exciting to me. So anyway, Thomas, I wanted to thank you for that part of history, and welcome you to Boise State.
Thank you all very much. I have been to Boise a number of times. Beautiful, beautiful place. But this is my first visit on campus, so I'm very glad to be here. And given the lateness of the hour, I wasn't sure if anybody would show up. I wasn't sure I was going to show up, but I thought that'd be poor form. I'm going to continue in the next half hour or so to talk about the challenges and the opportunities that are facing the future of high-end computing. Sort of the other end of the HTMT project that Richard mentioned. Let me just say a word about the HTMT project. It was intended to be a failure. If you can spend $4 million, $5 million, I guess that's not a failure, right? You invested much money. But if there is a student here? I am so glad that you folks are here. Thank you. If there's a student here, there is a life lesson in this. I didn't want to do HTMT. It was during a time when we were looking forward towards petaflops computing. Had no clue how to do it, almost had no clue how to spell it. And was a little questioning what it really sounded like. There was some misgivings there. And some people from NSF, from NASA, from DARPA came to me and said, would you find someone to do a project about diversity in technologies? And I said, yeah, okay, I'll look. Actually. But when they asked me, did I find anybody, I said, no. They then asked me, well, did I know how to do such a project? And I said, well, in the hypothetical, sure, but I have another project I want to do, and I'm writing a proposal on that. This is for an NSF grant. And they said, oh, that's not a problem. Here's a life lesson. Okay. That's not a problem. If they're both selectable, we'll fund both of them. So anyway, I wrote a proposal for what I couldn't care less, so I did a terrible name, HTMT. You know, it's not like you do that. Of course, when I named Beowulf, it was a complete accident. I was desperate to find a name. I had no idea. The person on the other end of the phone who insisted on the name now, I said, oh hell, just call it Beowulf. Nobody will ever hear of it anyway. Another life lesson for a student. I said, HTMT, well, okay, I'll do it. Yes, they were both selectable. No, they didn't fund both of them. And my pet project had to wait another 6 months to be funded by DARPA. Best mistake I didn't make. Right? This project, which worried about the extremes of cryogenic technology at 4 Kelvin, they used to be really impressive, by the way. 4 kelvins. If I were going to take any time to talk about quantum computing, I would tell you about 20 millikelvins. And people would say, oh yeah, right, 20 millikelvin, that's cold. Yeah, it's like 4 Kelvin is embalming with palm trees and so forth. Back then they said nobody would do this because you need the third pipe with the liquid helium. And well, in fact, Richard was right. It proved to be one of the most interesting projects I've certainly ever been involved in because it forced on us a point design, an area of consideration with such extreme demands that it required a completely different perspective on how computing would be managed, how such things as latency would be handled, what were the problems with overhead, what do we do about contention. These things were operating at 100 gigahertz. You know, a gigahertz is about so big, so that's like 100, all right? Fraction of a die. No, seriously, it was quite something, and we did spend millions of dollars, and many people today, including Richard's advisor, Peter Kogi, routinely refer to this as pretty much the best time we have. I consider myself the most expensive student in computer science. Most people don't demand several $1 million over a small number of years. So what I want to do is a little presumptuous of me, maybe even arrogant, but I would like to come back and look for a moment at what the underlying assumptions are that without even consideration we just accept. And as a result of this, that we continue to design machines in a way that is not just awkward and inconvenient, but downright inefficient. And we've been doing this for the better part of 20 years, and dealing with it pretty well, but it's getting worse with the end of things like Moore's Law and Dennard scaling. Then I'd like to talk a little bit about an alternative way of looking at computing that our team and some other teams around the country in slightly different versions are looking at a set of concepts as well, and what those implications are for computer architecture. I'll show you some results, and then finally I'd like to summarize by talking about, and of course these things are mindless, but what would a core architecture look like if we actually thought about it and took into consideration these things. So everyone needs an introduction, and the second bullet is the key issue. I'm closely associated, this isn't always a good thing, with the Department of Energy's planning process for the upcoming Exascale computing initiative. Now, I'm going to use the term exascale. I'm sorry, it's a buzz phrase. I will synonymously use the term extreme scale. But the truth is, if you looked at my history, you'd see I'd be just as excited about petaflops, some 11 years ago, and before that, just excited about teraflops. So these factors of 3 orders of magnitude just keep, well, it's job security. The nation, and by that I mean the United States, there are some other 200 nations, so I shouldn't be too specific here. The nation has decided, and the fact that the White House and Congress can actually agree on something is pretty scary, but that we will proceed with technology, software, hardware, algorithms development to, it'd be nice to say to retain our leadership, but it would be more accurate to say regain our leadership in the high-speed computing arena. Now, this is not just a race. This is about end product science, end product technology and engineering, social issues, and even those of national defense and security. And so these are things that are very important, and I can give a whole talk on that. I don't want to convince you that the next generation of supercomputing is necessary. I want to talk about the form and function of its elements. So to be safe, the nation is going to follow 2 paths. One, evolutionary, incremental, take the programming methods using things like MPI and OpenMP, and add things to try to expose more parallelism, because by the way, we need a billion-way parallelism. Yeah, that was billion with a B. And we don't know how to do that. Largest number of processor cores in a computer is about 3 million. So we're just off by, I don't know, 1,000. And yet we think we're going to be running these things at the beginning of the next decade. So in addition to evolutionary, we needed another term, the opposite of evolutionary. I made some proposals to my colleagues at DOE. I said, well, and I mean no offense to anyone, forgive me, but it's late and I'm tired. I said, the opposite of evolutionary, well, that would be creationist. I said, so we should talk about the creationists. Now, for whatever reason, they declined my suggestion. I said, well, there's a much better name anyway. I didn't mean that. Intelligent design. So we're going to have closed on is path and ISA for that. So the second path is, in fact, exploring the one I'm about to outline. So this isn't some pathetic old man. Okay, it is a pathetic old man, but it is not just a pathetic old man giving you his pipe dream. This is the path that will be pursued that is already, in fact, being sponsored by numbers of contracts from the Department of Energy, from the National Science Foundation, in the past, so not presently, by DARPA. And this is the path that the nation is going to proceed on. The details are highly controversial, and everything I say is my own personal opinion, and don't walk out of here necessarily believing anything I say. Right? Yeah. All right. Now, picture's a metaphor. An important point to be made. So 2 points here. First, everything is the same. Second, everything is different. Okay? Well, let's start with the first one. Everything is the same. So no matter how much people get up in front of you and tell you, we're using SIMD or we're using GPUs or we're using vector processors, and it's gone on for years, the truth of the matter, they're all derivatives. It was a nice, cute hack. They're all derivatives of the von Neumann model. In the 30s and 40s, several people made fundamental discoveries. I'm missing one, which would have brought us up to 5. You may have your own favorites. But Alan Turing and, of course, Church at Princeton solved Hilbert's last problem. Norbert Wiener looked at the problem from a quote-unquote cyber. You may wonder where cyber came from. It was Norbert Wiener from MIT. How to close the loop. How to have a feedback that allows you to adjust in control theory. Claude Shannon, whom I had the pleasure to meet on the 100th anniversary of the I guess it was the electrical engineering department at MIT. I was still a graduate student then, and very elderly, stately gentleman was there. Who am I forgetting? And John von Neumann, to whom we attribute the idea of the von Neumann architecture. Now I have to pause and mention a couple of things. Okay, so Norbert Wiener. Norbert Wiener, it wasn't Einstein, it was Norbert Wiener who was the classic archetype of the absent-minded professor. There's a story, no doubt apocryphal, but Norbert is apparently moving from one place in Cambridge to another place in Cambridge. His wife tells you when you come home, don't come back to the old house, come back to the new house. You know where the story is going. He comes back to the old house. Only then, when the house is empty, there's no furniture, the smart guy, he figured out he had moved. Right. Fortunately, some young girl came running by, and he said, well, do you know where the Wieners moved to? She said, yes, of course, Daddy. then there's the story of von Neumann. John von Neumann, extraordinary mathematician, one of just many, a whole influx of unbelievable people who came to the U.S. In part due to the horrible, horrible things going on in Europe. Now, von Neumann, who's given credit for the architecture, you may wonder why. Did he do the architecture? No, actually. Well, he did it with Eckert and Mauchly. But what he did do is on a train ride from Pennsylvania to Los Alamos, he had a lot of time on his hands. We don't have that kind of time anymore. And so he wrote the paper. But he must have run out of time because while he had enough time to put his name on the paper, he didn't put Eckert or Mauchly. In the field of computer architecture, the #1 prize is the Eckert-Mauchly Award, not the von Neumann Award. However, nonetheless, be that as it may, it was certainly a precedent setting, and we have largely guided much of our computing based on the fundamental premises of the von Neumann model. Well, von Neumann, brilliant, did other things as well. And one of the things was, in 1949, he developed another computer. You may even know about it. It is cellular automata. Those cellular automata, indeed, was devised by and proved to be Turing equivalent, although von Neumann hated that, because he really wanted to be von Neumann equivalent. But nonetheless, it was Turing equivalent. So the true history here is simply that while von Neumann did not invent the von Neumann architecture, he did invent quite possibly the most important non-von Neumann architecture. Okay, you can't make this stuff up. It's true. Key issue here is right up until, well, I say 2015, but in truth, I would actually move it back as much as 10 years, that all of the advances in supercomputing that we've undertaken to match the comparable advances in technology technology have still ultimately in architecture at their core been von Neumann derivatives. Nonetheless, they've been important and significant advances. So this is my time chart of the history from the beginning of the 1940s when, well, you know, I spent several years in Cambridge at MIT as a graduate student. There was this other school. Its name skips my mind. Harvard, yes. And so Harvard professor there, Aiken, developed what I'm told is still has a record for being the heaviest computer ever built. It was electromechanical, and IBM built it, and it was successful, and it was in computing at the rate of 1 operation per second, which you might think, you know, you could do pretty well like that too, especially with an abacus or equivalent unit. Now, it's not that he wasn't imaginative, but it is true that Charles Babbage had pretty much figured out that design more than 100 years before. Couldn't make it work, made a simpler version work, couldn't make it work, but was able to at least design the concepts. This was a short-lived, and I'll use the term simply a success, because in fact others also built mechanical computers. Name escapes me, I should know this. Zuse in Germany built some very successful machines. Germany built good computers. When I was an undergraduate student in the 60s, I had the German slide rule because somehow I didn't think an American slide rule would be good enough. 2 significant digits and change. By the end of the 1950s, modern computing had been on its way. Vacuum tube based, the invention of the core memory, and I'm sorry, this sounds like an MIT intensive talk. It's not intended to be. But the core memory was developed at MIT during the Whirlwind project, and J. Forrester. That was important technology for the next 25 years. By the mid-1970s, we had gone from 1 kiloops per second to in excess of megaflops. In fact, in the late 60s, we hit 1 megaflops of CDC 6600. And by the time that small-scale and medium-scale integration pipelining was able to be exploited, indeed was needed, and the Cray 1 that was developed based on some ideas prior developed at CDC was undertaken. And it was breakthrough. Peak performance of over 100 megaflops. Sustained performance on many applications somewhere on the order of 40 megaflops. The key idea here is the technology changed, the architecture concept had to change, and the execution model, the abstraction, the paradigm of how we organize computation, organize the programming, organizing the system software, and organizing the architecture to interoperate. And that's the key idea here. If we go on, we get up through the SIMD era when LSI, and LSI had a schism. By having large-scale integration, yes, you had some very small but not terribly useful microprocessors, good for controllers, but you were able to build both SIMD array processors, very simple processors, each working on its own data set with a stream of instructions going to all of them at the same time. SIMD is still, in its own way, a truly elegant model, but suffers from second and third order effects, which reduce, the efficiency and sustained performance. Nonetheless, you'll find SIMD operations in many of your microprocessors used for certain classes or certain patterns of data flow and execution. By the 90s, the VLSI, the killer micro, had become clearly a trend in the future. This is the, on the top above the 9091, this is the Intel Delta prototype for what became Paragon. A similar class machine, the red box on the bottom, became the first teraflops sustained machine. This at Sandia National Labs. And you go on, in the lower left is a 40 teraflops machine of the Japanese. All of these were microprocessor based. Many of these with special purpose or design products. The upper right, that was thinking machines. Thinking machines was a company that, well, here it comes again, spun off from MIT to build something called the connection machine. It wasn't going to be called thinking machines. It was going to be called International Thinking Machines, and ITM. And its motto was, when we say thinking, we mean business. Somebody, somewhere in New York, didn't have the sense of humor. You can figure out the rest of the story. Now, this case is just before now, and here is now. This is two of the fastest machines in the world, in fact, measured by the Limpac benchmark, or I should say more accurately, HPL. This is on your left. That is a Tianhua 2 in People's Republic of China. This is the fastest computer in the world. Peak performance, something in the excess of 50 petaflops. The same performance, again, against the Limpac benchmark, just over 32 petaflops. Logarithmically, that's halfway to the next exaflops. And the machine on your right is Titan. This is the Cray-built machine, which has a lot of GPUs. The first machine does not have GPUs, although its predecessor in China did. This has a lot of the Intel Xeon Phi, highly many-core chips there. And they're about half. One of the scary things about this is that if you include cooling, the Chinese machine consumes over 24 megawatts of power. Now, a highly subjective threshold of pain by the U.S. is about 20 megaflops. I say subjective because it's not based on some foundation. It's based on cost. A megawatt year is about $1 million in the U.S. If we had something, well, on Titan, we have something like, there it is, 8 megawatts. It's $8 million of operating costs just due to the power. The design for these two machines is the current generation of design, combining multi-core chips, that is to say, multiple processors per chip, plus accelerators, GPUs for relatively special purpose information flow. Titan is at Oak Ridge National Lab. And this is sort of where we are. Now, some future machines which are just being announced that move forward up into the 100 petaflops region are really not terribly different from these, except they cost more and they consume more power. Power, you see, that has become a key issue here. So this is actually data, and where to do. The actual data points come from the top 500 list, which is assembled on a semi-annual basis by Eric Strohmeyer at Lawrence Berkeley National Labs, along with Horst Simon and Jack Mangera at the University of Tennessee at Knoxville, and the late Hans Mauer in Germany, Mannheim, Germany. And the key point here, these are the top 10 power costs, and it's around 2004, 2005 that you can detect a very severe change. And this is when we started in the new epoch, the new era of computing, where in order to get more performance, we couldn't, in fact, get faster processor cores because the power couldn't go up per core, something about melting silicon. It's a serious issue. So instead, we had to keep the processor speeds, the clock rate, and so forth constant. There's also an issue about instruction level parallelism, which I won't go into, and instead increase the number of cores. So we now have, in order to achieve performance along an exponential line that we've become also happy with, and often is referred to as Moore's law, although it has almost nothing to do with Gordon Moore's observation, which was about DRAM density. Nonetheless, you see that suddenly the amount of parallelism we need in order to exploit the highest speed processors on a per application basis is growing exponentially. This is not good. This means, for example, that there are many problems, increasing number of problems, which are unable to, in fact, use this generation and future generation supercomputers because the way that they are programming them doesn't allow them to expose and exploit sufficient parallelism. And so far, I haven't said anything you can argue with me. So let's see, lesson for students. When I can't think of a good idea, I'll settle for any idea at all. And most people won't figure out that whatever it is not a good idea. And they'll eventually figure it out, but I'll be on to some other bad idea. It doesn't matter. And I'm serious about this. When I need a good idea, I say, what are we doing? And what is the opposite of that? Wherever that takes me mentally. What is the opposite? What is different from the current methods? And so I put together a list at the request of someone Singapore or New Zealand or something. Actually, yeah, all right. And I tried to come up with all of the assumptions that are true now and have been true for the last decades that we don't even question. We assume that wherever the solution is, these will be invariant. So let me just quickly run through these and then pick a few of them at occasion. So the first one, most important, that the floating point arithmetic logic unit is the precious resource. When I was young, that was true. When I was young, a 1 bit of an ALU with accumulator was like about this big. I've seen them at the Smithsonian and the Computer Museum. When I was an undergraduate, they were this big. This term is not vacuum tubes. Look it up. This is a transistor. That's why you think transistor is a 3-pin integrated circuit. And there were times when the whole architecture concept was designed and optimized around keeping the floating point ALU busy, maximizing the highest utilization. Look at the architecture. I'll come back to this in a moment, but let me run through the other one. The next one is, my favorite, is, everything has to be von Neumann. Either exactly like von Neumann or some variation of von Neumann. There have been plenty of research of alternatives. I had dinner with Jack Dennis last week for another symposium someplace. He's the father of data flow computing. Now, in truth, data flow is a deep abstraction that has many values. The assumed implementations weren't so deep, actually they were broken. But nonetheless, the underlying concepts were exceptional. That's only one of a number of possibilities. The control is sequential. You know, how do you get parallel computing working? Well, we assume we start with a sequential program and find a way to parallelize it. You know, physics doesn't work that way. The universe kind of figured out, well, everything is parallel. And then it gets narrowed down and it's sequential. We have managed to completely warp and distort physics, but we found a way to do it. Node performance is optimized just like the ALU performance. The assumption is if I want the fastest computer and I'm going to build them out of nodes, I want to build the fastest nodes. That's okay, unless of course you're getting 7% efficiency, which by the way is typical, and on a good day. Let's see some other ones. Oh, I love these. Binary values. What do you mean? Zeros and ones. I showed you a picture of Claude Shannon. He invented the bit, right? 0 and 1. Well, along with two-state Boolean logic, you don't have to do it that way. In fact, Boolean logic has multiple sets. It's not just two bits. There are multiple other sets that you could do that. And if you could build a higher level, remember this goes to the polynomial, or 2 to the n, then maybe we could actually get more information and more work done in smaller space. But yeah, there are a few crazies who are off in different clubs that nobody listens to, who worry about multivariate logic and numbers. We don't even consider it. Fixed length instruction set. There's another little group of weirdos that you'd be embarrassed to be caught with who worry about varying the length of the instruction set. Now, in truth, vendors have been forced to change the length of the instruction set, including places like Intel and so forth. But in fact, we did some studies that, to our surprise, shows if you actually take out the redundancy of the instruction set, use ideas which other people have promoted in the area of compression, but then continue to go forward and increase additional information such as tagging registers and keeping, it's a simple idea, and just keeping the type information of the data in the register instead of every instruction telling that register what type it is. I know, I remember this. All right, well anyway, you can get down an average instruction somewhere between 4 and 5 bits without in any way reducing the richness of the semantics of the instruction set. But that means that we have to be able to interpret that instruction set. And everybody assumes that it's x86. You can read the others. The bottom one is that we will use communicating sequential process developed by Tony Hoare in the late 60s, eventually adopted, known as message passing, and MPI, which was actually a major accomplishment by the community in the early 90s. to find a common framework and syntax for sharing. These are all assumptions that dominate today's supercomputers. None of them, in fact, are required. Let me just talk a little bit more detail about a couple of these. Well, I mentioned this adherence to the notion that the ALU is the resource to optimize for. Now think about it. Look at a chip design and understand, oh, what am I doing to get that? Well, let's see, I have a cache hierarchy in there. Why do I have, isn't cache hierarchy part of the memory architecture? That's not about front. Yes, of course it is. The purpose there is to have the minimum latency, maximum bandwidth, assuming data reuse. Right. Large part of the chip committed into what? To ALU utilization. What else? Well, there's branch prediction. Rich talked about branch prediction briefly. I don't remember why he did that.
Nobody studies it anymore.
Hence, worth mentioning, yes.
It was the most important problem about 15, 20 years ago.
Well, yeah, Pat did get the Eckert-Mockley Award for it, so that's true. He was as surprised as the rest of us. Speculative execution? Well, let's run 100 different in-flight requests, and maybe we'll hit with 2 or 3 or 4. Yes, you can find special problems that will really purr, that will do well. But on average, you know, the ILP, instruction-level parallelism ideas that were published, I remember really a lot of publishing out of Berkeley and Stanford. And 1,000-way parallelism. You know what the average ILP is? It's something like 2.7 on a good day. Not 1,000-way parallelism. Prefetching and so forth. And there are alternatives to dealing with it. The most important, I think, the most important measure, which has to involve power and energy, is in fact the memory bandwidth. Now, no, someone could argue that with me, and I'd be happy to go in that. I'm trying to find a cost-effective function. But the last thing I care about is the percentage of my ALU. What I really care about is my control state. How many threads can I keep active? I don't need a whole process to do that. I need a tiny little sliver of logic to do that. And I can have lots of it. And am I doing that so that I can keep time sharing the ALU? No. It's the network, which is most expensive in power and otherwise, and it's the memory bandwidth. So we should flush that. Well, I also mentioned the von Neumann architecture and keeping it busy. And there are a number of variants that are associated that we use and have used for the last 50 to 60 years of the history. But there are alternatives. DAGs. So DAGs are being examined now. These are directed acyclic graphs, both in software and in hardware implementation. It's basically a data flow, a little bit different, but in all cases, it's basically defining the precedent constraints of the operations separately independently, as opposed to worrying about the global barrier that we use in what's known as Leslie Valiant at Harvard, remember Harvard? Bulk synchronous parallel. Systolic array is another version, and I don't remember why I threw Who News. I was with John Gustafson, who's just published a book on his idea of how to do math, which, if he were right, I'm not qualified to say that he is, but I've known John for years, and he said it's on but this allows us to, again, relax. By the way, that's von Neumann on your left, and Oppenheimer on your right at the Princeton Institute for Advanced Study. Now some others, the Boolean logic binary values, we do not need to be restricted to two-state, either for the numbers or for the logic. There are higher order logic. Honesty demands that I at least repeat. Bill Dally, formerly of computer science at Stanford, now chief science at NVIDIA, tells me, and whom I argue with Bill, tells me that in fact it has been shown, some unnamed source, quote unquote, that the base 2 is still energy optimal. I've tried to work that out. I can't work it out, but I just wanted to tell you. We talked about instructions, and the fact is, imagine if you could do an instruction in 4 bits. Now, sometimes instruction is very large, but it has to do with the statistical distribution of which instructions are used most. And so you don't have to store an instruction in an instruction register. You can store a whole inner loop and not have to constantly access it. You improve storage, you improve latency, you improve bandwidth, and you reduce energy. Now, as I recall, all those are really good things. And I won't say anything about Intel ISA. I mean, let's face it, when they had the 860 to 64-bit architecture, they spent billions on that. Billions. And it was successful in the sense that they chased other vendors from doing their own architecture. But of course, when they were done, they had a processor that was twice as fast as the x86. Of course, that was after AMD did the Opteron. They did have to add 64 bits. That was a little bit embarrassing, but it still worked. When I was a very young child, there was a box of memory made out of little magnetic cores with wires going through each little core over here. And over here, probably the rest of the room, with a vacuum tube computer system. And there were wires between the two. Okay, vacuum tubes, core memory. Done with those, guess what? Go on your board, you have two chips, or two groups of chips, your processor with multiple cores, separated, wires on a motherboard, and a bank of memory. You'd think we would have learned by now. That's no better way to honor John von Neumann for his contribution. We refer to that as the von Neumann bottleneck. And it is the fact that the number of transistors on a die grows exponentially, again, according to Moore's law, but the number of pins don't, nor does the speed per pin increase. So we get into more and more stranglehold. Students love to show papers, publish papers, do projects, and showing, you see, I reduced the number of cores I use and the performance went up. Yeah, well, you're not task crashing, you're not starving with contention over the pins, and a whole lot of other things. Silicon-based semiconductor. So they laughed at me. I don't mind people laughing at me. I mind it when I'm not making a joke. Right? So single flux quantum gates. Okay, yes, super cool to 4 kelvins, niobium technology, easier to manufacture than the transistors we do today, by the way. Laboratory repeatable evidence over 700 gigahertz. Not for one device, but for complete logic collections. 700 gigahertz. Casual day, 100 gigahertz, sure. One of the few bragging rights I have, and this shows you my desperation, I have had, in 1997, I had the fastest logic that had ever been on the floor at the annual supercomputing conference. Fastest logic that has ever been on the floor since then. It was a superconducting technology developed TRW and SUNY Stony Brook. I don't remember how I managed to capture the credit for this. There it was, sitting there in a big Dewar, gas coming out. Fastest logic, people would come over, look at the meter, 270 gigahertz at that time. Pretty neat. Well, it wasn't neat. Unfortunately, so did the, where was this? San Jose, yes. Some of the San Jose fire marshal. Now, he's well-intentioned. He came over, he saw, in his mind, smoke rising out of the Dewar. He was afraid that this was dangerous. He was worried about a fire hazard. I said, sir, because I'm very polite, I said, sir, first of all, it's 4 kelvins. Nothing that close to absolute zero temperature is going to ignite anything. Secondly, it's a noble gas. It won't combine with anything. We ended up paying a fine. I don't It wasn't the first time I've had to pay a fine in supercomputing company. Okay, so as we move out towards the future of stream scale or exascale computing, recognizing that there are a number of opportunities that are simply not being explored, not being undertaken, then we can consider in those conditions, we can consider the alternatives. And the fundamental alternative, this is now an opinion, the fundamental alternative is the paradigm by which we do compute. not vector, it's not SIMD, it's not single issue, and some others. We need something new. We need to address the challenges of latency, indeed the variability or uncertainty of the latency. We refer to it as asynchrony, the irregularity, and they will sound like the same thing, and non-uniformity in time, irregularity in space. The computations, where not only does the programmer not know what's going on, the compiler can't figure it out. And that, therefore, systems that have built in what's referred to as introspection, the ability to watch itself, to be self-aware, and to make on-the-fly decisions of resource management and task scheduling. This is something we don't take advantage of. Remember, we're throwing away, in our execution pipelines now, we're throwing away 9 out of 10 operations. So we need to get some of those back for efficiency, but worse than that, so far we use either very coarse grain or a little bit of fine grain parallelism. Well, that's insufficient to expose the concurrency necessary to fill 1 billion threads, at least 100 million cores, and probably much more. This is a cartoon of a simple execution model in which the little wiggly lines, you'll think of them as threads. In order to publish papers, we have to make up new meaningless terms. So we call those compute complexes. Think of threads. Actually, a complex is slightly more sophisticated. Internally, it incorporates a fine-grained parallelism in the data flow fashion. Those arcs with arrows at one end are message-driven, not message passing, but message-driven computation. The ability to move work to the data when it's appropriate, rather than always having to move data to the work. We go further than that. We don't just move data and work, we move the control state. The ability to build a whole other layer of control, parallel control state. The use of continuations to the specific term. And finally, for different classes of resources, like GPUs, heterogeneous computing, we not only move input data, but we have to actually be telling it what it's going to do. And so another methodology, actually first developed originally for HTMT, notice percolation. It's a variation on message-driven computation. I don't think anything I've just said is absolutely original. It's independent, but it's not original. The synthesis, however, is. And there are some details which I don't have time to talk about that are both original and independent, and will probably make, in my opinion, a big difference. So here's the state diagram for a compute complex, aka a thread. No, don't get concerned. I'm not going to go over every bullet. In the blue is inclusion and recognition of the software substrate known as the runtime system. This introspective, self-aware aspect above the operating system, below the compiler, that allows the system to, on the fly, make best use of its resources, and with more sophisticated priority policies, to actually order the operations that need to be performed to get the best overall behavior. You cannot build an optimal execution stream this way. Not only is this an NP-hard problem, but it's a causal problem. So you have to know the whole future before you can even optimally do it. However, you can get really close in many, many cases, although one could contrive a problem that will break this. The only circle I really want to talk about is that D circle. This is the discovery of this project. The D circle stands for depleted thread. Well, you're not unfamiliar perhaps with the idea of a suspended thread. The thread that for one reason or another can't go on with the computation, but can be put aside for a short period of time and some other pending problem go ahead, so you get non-blocking of the resources. That's fine. But when you're in a condition where that suspended thread is really going to have to wait a while, you need to get out of the finite resource set provided by the runtime system, and that's the point of the depleted thread. Now that may seem to you like a much ado about nothing. Here was a discovery. You know it's a discovery when you see something, you know it's wrong, and you try to find the bug. In the end, it wasn't wrong. Lesson, students, still late? Okay. When you move from development of a new thing to discovery of a new space, whether by intent or being forced to, you are now at another plane of research. We reach a point where the model creates itself, tells us what it needs to be. Michelangelo, in creating the statue of David in Florence, said, oh, I didn't do anything, it was there all the time, I just removed the excess stone. That also may be apocryphal. Michelangelo was not known to be modest. But in a sense, that's the same thing in such an abstraction like this. There are other issues with mass storage, with reliability, even real-time semantics. It's ironic, isn't it, that supercomputing, which is more associated with time than just about anything, doesn't actually have, in any of its current models, semantics of time itself. Okay, big mistake. Required by contract to show you a giant, closely meaningless stack. But in the middle, you'll see something called runtime systems. User thread, global address space, synchronization, communication, and introspection. Words that I have been using. At the bottom of the hardware, and at the top are other things that other people care about. It's that runtime system that is the magic that people are developing now. Those of us at Indiana University, some of our colleagues at Louisiana State University are working on implementations, completely different software stacks, of the runtime system HPX. None of us remember what HPX stands for, but at Rice University is OCR. Intel pays close attention to that. Stable at Texas A&M. Term++, probably the oldest runtime system in HPC and Illinois, and well, you can read the rest. Real buzz on Legion right now. They got a couple of problems to work very well at Stanford out of Lawrence Livermore. Block diagram of our runtime system architecture basically shows software functionality that implements each of these major ideas. The thread management, the global address space management, the event-driven computation and synchronization, and the efficient use of the local control objects, or the synchronization that I talked about before. And I actually talked about all this. You know, I shouldn't do that, right? Okay, let me just say, what's really cool about my work, and therefore you can ignore everybody else's work in the field, is not only is it brilliant, but it's based on the underlying abstraction of an execution model. In an execution model, yes, it's an abstraction. You're uncomfortable. You can't get your hands around it, right? But how do you talk about a full computing system? You can talk about the compiler, you can talk about the architecture, you can talk about the programming model. But tell me what the vernacular is. You're talking about the whole system in a uniform and in a unified fashion. Well, that is the execution model. We're uncomfortable with it, but it's what you need. It talks about the functionality and interoperability of the different layers of a computing system. The second thing is that if you're building something that's supposed to be high performance, maybe you should be worrying about performance. And so an execution model that doesn't embody the principle of a performance model, in our case it's slower, an acronym for starvation, latency, overhead, this was a stretch. Waiting for contention, it worked. Energy and reliability. And these are quantifiable metrics, performance model, whole other talk, but they pay you for it, so that's good. Message-driven computation with continuation. There are many examples prior to our work in which there were variants of that. I think ours is the best. Okay, I'm coming close to the end. The really neat stuff about this is not how well we continue to process matrices, arrays, vectors. That's old school. What this is designed to do best is to process graphs. Vertices with links to other vertices. Irregular, time-varying, distributed in a way entirely non-uniform and unpredictable in many cases. Richard is the father of the Graph 500, which is a major part of the kind of thing I'm talking about, although not yet dynamic graphs. Right? Okay. Big credit to this guy. The second is being able to distributed control operations, atomic operations, spread over entire systems. The use of LCOs in graphs allows you to manage graphs in a distributed way. This is actually pretty heavy and cool stuff. I mentioned already the depleted threads that act like synchronization objects, completely the same semantics. And now how do I do this? So anyway, we built all this. We've done cool stuff. This is a gamma ray burst simulation using highly dynamic adaptive mesh refinement that shows gamma rays. It's probably the most energetic phenomena in the universe, save the original Big Bang itself. Of course, this would be embarrassing if it doesn't actually work. Here, come on. All right. That is very cool. That completely died. It has never done that before. Cosmic rays, what altitude are we? One more time, and then I'll just slash my wrist. Okay, you would have been so awed, it would have been the best visualization you have ever seen. You have. Yeah, thanks a lot. Okay, now I'm going to humbly try to slink away with just a couple more slides. So understanding the trade-off space is very complex. This was a queuing model that was performed by one of my doctoral students to understand the comparative value of the classic or conventional blocked message passing versus the non-blocking dynamic adaptive message-driven computation. This is just one possible way to look at it. But there are two things that you can take away. So the horizontal axis is the number of cores per node. Basically, how much parallelism do you have? And the amount of overhead, the average amount of work it takes to manage this parallel resources. And the vertical axis is the performance gain. It should be pretty clear that there's a plateau. And working with that space, you have approximately the same advantage. But if you hit the tipping point, and this is in two different dimensions, you go south big time, really fast. This kind of study tells us where the optimal regimes of design are and where to avoid them. This kind of study is not typical within the HPC community, but it's actually very important and highly revealing. Okay, so just so you all go out and say, God, that's an honest guy. So maybe I don't have to be honest. What, did we have enough money in the meter? I don't have to recover from this. This is a disaster. Not all programs are structured, configured, have the algorithms that will yield to the opportunities that I've been discussing. Some problems are very uniform and highly regular. And frankly, the way we're doing them is likely to be pretty close to optimal anytime in the future. And I was going to show you a graph, seriously I was, that showed you that we were barely as good as the conventional practices. Now, how many people get up in front of you and show you the dirty laundry, right? Well, I was going to do this. Then I was going to show you, this is a wonderful graph, two neutron stars orbiting around each other, creating gravitational waves to be detected by the National Science Foundation's most expensive scientific experiment known as LIGO, for Laser Interferometric Gravitational Observatory, to measure the core actions in the fabric of space-time, built well over 10 years ago. 10-year review. How many events did you see? 0. NSF took the appropriate professional action and gave them more money to measure 0 to more significant digits. I should have such a job. The future of high-performance computing is very important for the sciences, for engineering technology industry, for society as a whole with big data in many different ways, and for security and national defense. Future supercomputers cannot be the supercomputers of the past. They have to be as new in the future as the old machines were new for their future. For whatever reason, there is a hesitation, a resistance to new ideas, legacy codes. We worry about skill sets. We worry about too many people retiring. We worry about the billions of investment. And these are arguments that we make, and then we look for stopgap measures. Oh, the cloud. Let's go get some computer somewhere on the internet. We don't know what it is. We don't know how it's built. We sure can't optimize for it, but we don't have to worry about it. creativity at the design level, at the fundamental, well, innovation. You don't know where it's going to lead, but you know where it's coming from. And those few students here, thank you for staying to the end of the talk. It's been delightful. Thank you very much.
Couldn't.
Questions? You know, one short, quick question, and then we can all go home.
This is wonderful work. This is like taking everything we've learned about optimization and applying it throughout. It's just great.
Well, you're not hopping on, I disagree. Clearly, he's a perceptive individual. And I appreciate that disruptive question. And in fairness, there are a number of groups across the country which are exploring for different reasons.
So my point is that it's not disruptive. But what you're doing is taking everything is well understood, all these things, and applying it in different ways to different parts of the system that we did not realize we could before.
The summary lesson, again, is that sometimes the biggest risk is not taking risks. And that's the condition right now. Okay, one other person, they just flatter me with a question. I cry easily. It would be embarrassing. Oh, just a second. You know, if I had any self, oh, thank you, sir. You're right, say, go ahead.
So you mentioned a lot of challenges that we are facing, but what it is that when we are doing Exascale and other things, there's inherent cost of communication and synchronization of data.
That's right.
So you have complete elements which are going to be somehow communicating. There will always be some inherent flaws. Are there alternate ways?
Yes, and there was this wonderful graph that, by the way, you didn't see, that shows the block diagram, not the software architecture, the hardware architecture, that shows exactly where those individual elements of overhead show up, and where the processors today don't have these, but because they don't think about anybody else but themselves. They're really rather subset. And, maybe a couple of guys next door because of cache coherency, but they treat the other, or they will treat the other billion cores as I/O devices. This is not optimal for the fact that they want to share the computation. And so, yes, I would like to say that I believe that research projects funded by the national government are moving us in that direction, but I don't think it's true. They're spending money, but I think that they're spending money on old roadmaps, not new opportunities to reduce it. Okay, I'm going to let you all go. Again, thank you all very much.
Thank you everybody for attending tonight, and I'm very thankful, and congratulations.
Yes.
Do you still believe that humanity will stop on 64 exaflops?
That's my story, and I'm sticking to it. And, because the number of using the conventional practice.